Good morning. Today we can do the problems on thermodynamics. So already we have two videos on thermodynamics. This is the third one. So today only problems we can do. What are the formulas we got? One is the Joule's law. Second one, first law of thermodynamics. dq is equal to du plus pdv. Third one, second law of thermodynamics, no formula, and heat engine efficiency 1 minus T2 by T1. Fourth one, coefficient of performance of refrigerator, that is T2 by T1 minus T2, where Q2 by Q1 minus Q2. Here 1 minus Q2 by Q1. Okay. Next, work done in an isothermal process. The work done in isothermal process 2.303 nRT log V2 by V1 base 10. The work done in adiabatic process 1 by gamma minus 1 P1 V1 minus P2 V2 or R by gamma minus 1 T1 minus T2. Okay. Next, adiabatic relations between pressure, volume, temperature. P V power gamma constant. Second one, P V power gamma minus 1 constant. Third one, P power 1 minus gamma by gamma constant. These are the adiabatic relations between pressure, volume, temperature. Next, work done in adiabatic isobaric process PdV. dW is equal to PdV. Work done in adiabatic process PdV. Internal energy, change in internal energy 1 by N Cv dt. N number of moles Cv dt or d theta. Heat energy dQ is equal to N Cp dt. Cp minus Cv is equal to capital R, and dW work done is equal to dQ minus du, that is nR dt. One formula, nR dt. Work done in adiabatic process, work done in a isobaric process, nR dt or pdV. Next, two gases are mixed. For mixed gas, Cp N1 Cp1 plus N2 Cp2 divided by N1 plus N2. And mixed gas Cv N1 Cv1 plus N2 Cv2 divided by N1 plus N2. So these are the formulas which we got in thermodynamics. Joule's law, first of thermodynamics, and heat engine, refrigerator, isothermal process, adiabatic process, and adiabatic relations between pressure, volume, temperature, specific heats of gases, Cp-Cv relations. If Cp-Cv are molar specific heats, Cp minus Cv is capital R. If they are gram specific heats, Cp minus Cv is equal to small r, that is capital R by molecular weight. Cp minus Cv, gram specific heats and these are molar specific heats. If we take molar specific heat, Cp is equal to gamma R by gamma minus 1, Cv is equal to R by gamma minus 1. Cv is equal to R by gamma minus 1, Cp is equal to gamma R by gamma minus 1. So, these are the formulas which we are going to use in this class, and we can do the problems based on them. For example, there are two gases, they have pressure P, volume V, pressure P, volume V. So, first gas and second gas, A and B, two gases. And first gas is compressed such that volume become half. Isothermally, in isothermal process, first gas is compressed, so volume become half. Second gas compressed adiabatically such that volume become half. Now the question is, for which gas the final pressure will be more? So let the final pressure in here is P, here P1. Which one is more, P or P1? So this is compressed adiabatically. So in adiabatic process we know P1 V1 is equal to P2 V2. So P1 and V by T. Therefore, P1 is equal to 2P. So this is P1 dash, this is P1, final pressures. In adiabatic process, this is isothermal process. In adiabatic process, PV power gamma constant, P1 V1 power gamma is equal to P2 V2 power gamma. Therefore, here pressure P, volume V power gamma. Here final pressure you have to calculate as P1 dash, final volume is V by 2 whole power gamma. V by 2 whole power gamma. Therefore, V power gamma cancel. P1 dash is equal to 2 power gamma into P. We got P1 dash is equal to 2 power gamma into P. That means final pressure here 2P, here 2 power something into P. So gamma is more than 1. So this value is more than 2. So that's why this pressure is more than this one. Therefore P1 dash greater than P1. That means final pressure of gas B greater than the final pressure of the gas A. Final pressure of gas A. Okay. So next one more problem. Note down. Note down one more problem. Monoatomic gas expanded such that volume increases by 32 times. Initial volume V, final volume 32 V. Initial pressure P, final pressure how much? Question is what is the final pressure for the monoatomic gas? Volume increased by 32 times. So this gas is adiabatically volume changed, expanded adiabatically, or suddenly a gas is suddenly expanded to 32 times of its initial volume. Then you have to take adiabatic relation P V power gamma constant P1 V1 power gamma is equal to P2 V2 power gamma. So initial pressure P, initial volume is V power gamma ante 5 by 3 is equal to final pressure you have to calculate V2, final volume 32 V whole power gamma. 32v whole power gamma. So r 5 by 3. So this v power 5 by 3, v power 5 by 3 cancel. Therefore final pressure is equal to initial pressure by 32 whole power 5 by 3. 32 whole power 5 by 3. 32 you can write 2 power 5. So P by 2 power 5 whole power 5 by 3. 5 not cancel. So we write down P by 2 power 25 by 3. So 2 power P by 2 power 25 divided by 3. So this is the final pressure. This is the final pressure. One more problem we can do. One more problem we can do. A gas obeys the law of PV power 2 is a constant. PV square is a constant. Now initial pressure is P, initial temperature is P. Temperature doubled. What happened to the pressure? Temperature doubled. What is the final pressure? So they given PV power 2 constant. First we have to obtain pressure temperature relation. This gas obeys this law. PV square is a constant. It is not isothermal, not adiabatic, some other process. Then PV square is a constant. And the general gas equation PV is equal to RT, you can write it. But we don't want volume. So square this one and divide with this. So V square cancel, 1P cancel. Therefore we get P square by P constant. P square coming numerator by P, constant by R is constant. Then T1 square by T1 is equal to T2 square by T2. Therefore, initial temperature T, final initial pressure P. Final temperature 2T, 4T square, 2T whole square, 4T square by P2. So T square cancel, P2 is equal to 4P. The final pressure becomes 4P. So whatever the gas law they given, we have to compare with the PV is equal to RT second equation, and then we can obtain the relation between other variables. So this model is one important model. Now we can mix two gases. 16 grams oxygen and 8 grams helium are mixed. Calculate gamma of the mixture. So 16 grams of oxygen. So oxygen molecular weight 32. So 16 grams means number of moles is equal to mass by molecular weight. So half gram. Number of moles is half, that is 0.5 moles. Oxygen diatomic gas. So Cp 7 by 2R, Cv 5 by 2R. You remember these values first. 8 grams of helium. So number of moles of helium, mass by molecular weight. So 2 moles. Number of moles 2. Helium is monoatomic gas. So Cp 5R by 2, Cv 3R by 2. Now these two gases are mixed. Then for mixture, resultant Cp is equal to N1 Cp1 plus N2 Cp2 divided by N1 plus N2. N1 0.5 into 1 by 2, Cp1 7 R by 2 plus N2 2 moles Cv 5 by 5 R by 2 N1 Cp1 plus N2 Cp2 by N1 plus N2 N1 0.5 at 1 by 2 plus 2. So R by 2 R by 2 N1 Cp1 plus N2 Cp2 by N1 plus N2. So capital R is 2 calories if you take. Capital R is equal to 2 calories. So 2 by 2 cancel, 2 by 2 cancel. So here we are getting 7 by 2. So 3.5 plus 10. 3.5 plus 10 divided by, so 2.5. So that is equal to 13.5 divided by 2.5. So 135 by 25. 135 by 25. So that is equal to 27 divided by 5. So that is a mixed gas Cp value 27 by 5. So what is units? Calorie per gram per degree centigrade. So specific heat of gas calorie per mole. You can take a mole. Okay. Calorie per mole per degree centigrade. So that is Cp or mixture. Similarly, you calculate mixture Cv value. Cv of the mixture. N1 1 by 2 5R by 2 plus 2 into 3R by 2 divided by N1 plus N2 by 2.5. So here R by 2 cancel because R value 2 calories, that's why cancel. So final answer also we expressed in calories. Otherwise in terms of R only you have to tell. So 5 by 2, 2.5 plus 6, 8.5 divided by 2.5, that is 85 by 25. So 17 by 5. Therefore, finally, gamma of the mixture Cp by Cv. So 17 by 5 by 27 by 5 divided by 17 by 5. 5 cancel, 27 by 5. Gamma of the mixture is 27 by 5. Gamma of the mixture is 27 by 5. Next problem, sink temperature 27 degrees centigrade, sink temperature 27, source temperature 227 degrees centigrade, calculate efficiency of the heat engine or Carnot engine. Efficiency 1 minus T2 by T1. Efficiency of the heat engine 1 minus T2 by T1. So that is 1 minus T2. Sink temperature 27, 300 divided by 227 means plus 273. So 300, 500. We are getting 500. So 1 minus 3 by 5. So that is 2 by 5. Efficiency 2 by 5 fraction. Percentage means efficiency is equal to 2 by 5 into 100. That is 200 by 5, 40%. Efficiency is 40%. Efficiency is 40%. Okay. Diatomic, monoatomic gas is there. Some heat energy supplied to it. In that, what percentage is utilized for work done? So, first of thermodynamics, dQ is equal to du plus dW. What percentage of this utilized for work done? dW by dQ into 100, how much? That is the question. What percentage utilized for work done? dW. That is 1 minus 1 by gamma into 100. 1 minus 1 by gamma into 100. So they said the monatomic gamma value 5 by gamma is equal to 5 by 3. So 1 minus 1 by 5 by 3 and 2 by 3. 1 minus 2 by 3. 1 minus 2 by 5. 1 minus 1 by 5 by 3. Na? Okay, 3 by 5. So 3 by 5 into 100. So that is equal to 1 minus 3 by 5. 1 minus 3 by 5 is 2 by 5 into 100. So 40%. The work done, the fraction, the percentage of work done utilized for the percentage of energy supplied utilized for work done is 40%. Is 40%. And the percentage of energy increased to its internal energy how much? And du by dq into 100 how much? That is 1 by gamma into 100. 1 by gamma into 100. Here 1 minus 1 by gamma into 100. 1 minus 1 by gamma into 100. So that is a percentage of work done. Next, we get a curve like this. P, T. We get a PT curve. So it is going from A to B. It is like this, the given. So what happens? It's a PV curve. So at which place temperature is more? From A to B, temperature increasing or decreasing? That is the question. PV graph. So here you take one line and let this angle is theta 1. Here also you make one line like this, make angle theta 2. So theta 1 greater than theta 2. Therefore tan theta 1 greater than tan theta 2. Tan theta 1 greater than tan theta 2. PV graph. So PV is equal to nRT. PV is equal to nRT. And here slope means P by V will come. Okay. So question is they can give like this PT graph. So curve is like this. At which place what happens to its volume? Volume is either increasing or decreasing. Volume is either increasing or decreasing, they can ask. So this is the problem. So slope is more at this place, slope is less at this place. So slope means tan theta is equal to P by T. P by T. So P by T is equal to inversely proportional to NR by V. Slope is more, volume is less. So slope is more at A. So volume is less at A. From A to B, volume increasing. Actually, PT graph. So from A to B, what happens to its volume? That is the question. So take it is not passing through origin. If it is passing through origin, P by T is a constant. So here and volume constant. At constant volume, we know that constant volume P directly proportional to T. So we get a straight line passing through the origin. PT graph like this will come. But here PT graph is not slightly not passing through origin. Then at A and B, from A to B, what happens to the volume? Volume increasing or decreasing? So at this place, calculate slope tan theta, and at this place, calculate tan theta. We know tan theta 1 greater than tan theta 2. Tan theta is equal to P by T from this equation. So tan theta is more, P by T is more. P by T is more, P by T is inversely proportional to volume. Volume is less. So volume is less at A and more at B. So that means volume is increasing from A to B. Volume of the gas is increasing from A to B. PV graph, area covered with x-axis gives the work done. Work done means you have to calculate this area. You have to calculate this area, work done. And sometimes they can give the graph like this. In a cyclic process, change in internal energy 0. du 0. Cyclic process, change in internal energy 0. That is one important point. If the curve is circular and that is given in anti-clockwise, then the work done, this area gives the work done, and anti-clockwise means work done negative. Anti-clockwise, work done negative. If the curve is clockwise, work done positive. Work done, we can calculate. If they given the curve in anti-clockwise, work done negative. Clockwise, work done positive. Clockwise, work done is positive. Next, suppose calculate work done like this they given. So here 2P, here is P, here V, here 5V. So we need the area of a circle. We know the formula area of circle pi r square, but here what we have to use is the area of circle, that is work done is equal to this area. So pi r1 r2, take this formula because radii is different size. Then pi into r1. So this is diameter 5v minus v, 4v. So 4v by 2. That is R1. What about R2? P to 2P, and then P. So 2P by 2. That is another radius. Then we are getting 2 times cancel, 2 also cancel, pi V P. This is the work done. This is the work done. Pi V P. Okay? So main concepts, mixing of the two gases, first of thermodynamics, and heat engine, refrigerator, and problems based on the graphs, and from slopes, slope of the graphs, that question also important. Area covered calculation, that gives the work done. That is one important point. And the mixing of the gases, the resultant gases Cp, Cv values, that is also one important model. These are the different problems on thermodynamics. Already zeroth law, Joule's law, and first of thermodynamics problems we done. Heat engine, refrigerator also done. So some adiabatic relations, isothermal process, adiabatic process relations, and main about graphs. In this class we discussed. Okay.